A common problem in introductory physics classes is the so-called day at the races problem, where a uniform object is rolled down an inclined plane. And usually this is a comparison between objects of different shapes. The most common one is a sliding block, a rolling hoop, a rolling sphere, solid sphere, and a rolling cylinder. For instance, this particular problem would have been a uniform disk. That's a cylinder rolling down without slipping on a ramp inclined 25 degrees, and the person is asked the speed at the bottom. But interesting is to watch what happens in terms of that speed and which one gets down if they're all started together. In the day of the races, the one that ends up with the fastest speed at the bottom is the one who wins the race. And we find that the only thing that is important is the shape of the object, not its mass and not its size. And this is done through the calculation by working conservation of energy. Let me show you an example of the demonstration, and then I'll explain the mathematics by which it works. In race 1, we have a sphere, a hoop, and a cylinder. Ready, get set, go. In race 2, we have two cylinders of different radii and masses. It's a tie. An important concept in understanding rotation is the moment of inertia. The moment of inertia for a uniform object can be written as gamma, some constant, times the mass of the object times the radius squared. For a sliding block that doesn't rotate, gamma is 0. For a sphere, gamma is 0.4, or 2/5. For a cylinder, gamma is equal to 0.5. And for a hoop, gamma is equal to 1. We'll see that the smaller the gamma, the less energy is tied up in rotation, and the faster the object is in the race. The higher the big gamma, the more energy is tied up in rotation, and the slower the object is in the race because it has less energy to do translation. The analysis of an object rolling without slipping down an inclined plane is based upon the conservation of energy, because at the point of instantaneous contact, the friction force has no displacement and hence does no work. The normal force, which is perpendicular to the plane, also does no work and is at the instantaneous point of contact. Gravity, which is not at the instantaneous point of contact and does work, but it is a conservative force. So since the work by non-conservative forces is 0, the change in energy is 0, and the energy is conserved. One can calculate the energy at the bottom, which is purely kinetic, using Giancoli's theorem, as 1/2 the mass times the final speed squared plus 1/2 the moment of inertia about the center mass times the final angular speed squared. And this energy comes from the gravitational potential energy that the object has when it's at the top of the ramp. All moments of inertia for these rotating objects can be looked at as being a gamma times the mass times the distance squared, where for the rolling hoop, the sphere, and the cylinder, this r is the radius. The gamma factor is 1/2 for a disk. It is other values for the other objects. 0 for a sliding block because it has no rotation. 1/2 for the disk is set, 2/5 for a sphere, and 1 for a hoop. If you put that into this I, then you find you have gamma m. You can combine the r with omega f, so you have r squared omega f squared, but there's the no-slip condition that says that the velocity of the center mass is equal to the radius of the object times the angular velocity. So we can replace this term here with the final speed of the center mass squared. When we put that in, this term on the left, both of these combine, and we end up with 1/2 the mass plus gamma m. I'll come back and talk about this term in just a minute. If we cancel the m's and bring the 2 to the other side, we find that the final speed squared is 2 times the acceleration due to gravity times the height, which is all the same for all of the objects, over 1 plus gamma. So the only thing that varies between the objects is gamma. It's not the mass, which canceled out. It's not the radius, which got combined in here with the angular speed to end up just being the translational speed. It just depends on this shape. And you, of course, can find the final speed as the square root of 2gh, 1 plus gamma. The square root of 2gh is what you find if you drop an object a distance of h, or if you slide a block down an inclined plane in one of the earlier chapters. So if you make gamma equal 0, you're talking about a sliding block. This would be true provided, of course, the friction force is not too great in the problem and there's not much energy lost in the sliding process, so that our conservation of energy argument is okay. For a sphere, gamma is 2/5, so we find that we get the same speed divided by the square root of 1.4. So our speed is less. If the gamma is 1/2, it's the square root of 2gh, now divided by the square root of 1.5. And if it's a hoop, it's the square root of 2gh over the square root of 2. So as the gamma gets larger, the speed goes down. Why? A larger gamma, if we go back and look where this came from, is in this energy of rotation. So as the gamma gets bigger, the energy of rotation gets bigger. If the energy of rotation is bigger, there is less of the energy left for translational energy, which is what gets the center mass to the bottom of the ramp. So all the energy is going into spinning around and around. None of it is using to move the block down the incline. So you want the gamma to be small. You want all the energy to be going down the incline, not spinning around the center of mass like a rotary saw. Another way to look at this is to say that the gamma m produces an effective rotational mass. So this is if you're moving translationally 2 blocks, one that's the regular mass you would expect, and the second which is a mass due to rotation. That's this gamma m term. The bigger this gamma m, then the more effectively, if you would, the bigger the total m. And the bigger the total m, the less you have in terms of v squared to have the same kinetic energy. So if you have a fixed amount of kinetic energy and you raise the m, the v has to go down correspondingly. Either way, the bigger the gamma, the slower the speed, and the slower the object will be getting down the incline. So the hoop finishes last. A sliding block, had we had one, would have in fact finished first. Alright, that completes this video.